this episode, we take the text representations you learned about and focus on the part that separates a useful natural language processing system from an impressive demo, which is evaluation. Text models can look surprisingly good on a held-out dataset and still fail badly in the real world, especially when language shifts, when user populations differ, or when the dataset contains hidden shortcuts. In cloud security and cybersecurity environments, this matters because text often drives triage decisions, incident categorization, and prioritization, and a model that misclassifies text can send teams in the wrong direction or create blind spots. The evaluation challenge is that language is messy, labels are often noisy, and the meaning of success depends on the cost of mistakes. That means you cannot rely on one score and assume the model is ready. You need to understand precision and recall trade-offs, how bias can enter text systems, and what common failure modes look like so you can detect them early. The goal is to build a practical evaluation mindset that keeps you honest about what the model can do. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Precision and recall are central because they describe different kinds of errors, and text systems often have to make trade-offs between them. Precision tells you, when the model predicts a category, how often it is correct, which matters when false positives create wasted effort or harm. Recall tells you, of the true cases that exist, how many the model finds, which matters when misses create risk or lost opportunities. In security triage, a text classifier that tags tickets as likely incident might be used to route work, and low precision could flood the incident response team with benign tickets, while low recall could allow real incidents to be buried in the queue. Beginners sometimes assume they should maximize both, but trade-offs are common because tightening the model to reduce false positives often increases false negatives and vice versa. The correct approach is to align the trade-off with operational goals, such as prioritizing high recall for severe categories where missing is dangerous, and prioritizing high precision where human review capacity is limited. This is not just a math decision. It is a workflow decision that must be made explicitly. In cloud security, where teams often operate under time pressure, the cost of wasted attention is real, and evaluation must reflect that reality. Thresholds are the mechanism that turns model scores into labels, and they are especially important in text classification because many models output probabilities or confidence-like scores rather than hard categories. A fixed threshold such as 0.5 is not universally correct because the right threshold depends on class prevalence and on the costs of false positives and false negatives. If a particular incident category is rare, a threshold of 0.5 may never trigger, producing high apparent precision because it predicts almost nothing but terrible recall. Conversely, lowering the threshold might improve recall but create many false alarms, which can overwhelm teams. Beginners often report precision and recall at a default threshold and assume that is the system's performance, but a more honest evaluation explores how performance changes across thresholds. In security operations, you may choose different thresholds for different categories, especially when some categories are high severity and others are informational. Threshold selection is also connected to calibration, because if scores are not well calibrated, the same threshold can behave differently over time. Evaluating thresholds is therefore part of evaluating the model, not an afterthought. When you tune thresholds thoughtfully, you align model behavior with real decision constraints. Class imbalance is common in security text tasks, and it can make accuracy a misleading metric even when the model seems to perform well. If most tickets are routine access requests and only a small fraction are true incidents, a model can achieve high accuracy by predicting routine most of the time. That accuracy would look strong but would not deliver the value you care about, which is finding the rare incidents. This is why evaluation should include class-specific metrics, such as precision and recall for the rare class, and should often include macro-style summaries that treat all classes more evenly. Beginners sometimes discover this only after deployment, when the model appears to ignore the rare class entirely, because the default training objective and default threshold encouraged majority predictions. In cloud security, class imbalance can be even more severe because severe incidents are rare by design, and text describing them can be highly variable. A correct evaluation strategy therefore focuses on whether the model is useful for the rare but important cases, not on whether it looks good on average. It also includes checking how many examples exist for each class, because extremely small classes can produce unstable metrics that vary widely across samples. Honest evaluation recognizes when data is too limited for strong claims. Bias in NLP can enter in ways that are not immediately visible, and in security contexts, it can affect both fairness and reliability. Bias can mean the model performs differently across groups of users, teams, or regions, and it can also mean the model learns patterns that reflect how data was collected rather than the underlying reality. For example, if certain teams write tickets with more detail, the model might learn to associate detail with severity, not because detail causes severity, but because reporting style varies. If certain regions use different terminology, the model might misclassify their tickets because the vocabulary differs from the training data. Bias can also emerge from historical processes, such as certain types of incidents being investigated more thoroughly and therefore labeled more consistently, which makes the model better at them and worse at others. Beginners sometimes assume bias only relates to personal attributes, but in security text, bias often relates to organizational and operational patterns, like differences in templates and jargon. Evaluating bias means checking performance across these segments, not just overall. It also means looking for proxy effects, where the model learns that certain names of tools, teams, or projects correlate with labels, which can be a shortcut rather than a true indicator. When you identify bias, you can decide whether it reflects legitimate differences or harmful artifacts. Another critical evaluation idea is to look beyond aggregate metrics and examine error types, because text errors often have patterns that reveal model weaknesses. Some errors happen because the model confuses similar categories, like treating an authentication failure as an access request, and those confusions can be addressed by clarifying labels or adding context. Other errors happen because the model is sensitive to certain trigger words, like seeing breach and assuming incident even when the ticket is about a policy discussion. Still, other errors happen because of negation, sarcasm, or context like not an incident, which bag-of-word style representations can mishandle because they do not model order or negation well. In security tickets, negation is common, such as not malicious or no evidence of compromise, and a model that misses negation can create frequent false positives. Beginners often evaluate by counting errors, but a more professional evaluation groups errors by cause, because different causes require different fixes. Error analysis also helps you set expectations, because you can explain which cases are hard and why. In cloud security operations, understanding error patterns can guide workflow design, such as routing uncertain cases for human review rather than forcing automation. Failure modes in NLP often appear when the environment changes, because language shifts over time in ways that structured data does not. New products, new attack techniques, and new internal projects introduce new vocabulary, and a model trained on older text can fail because it has never seen those terms. Ticket templates can also change, and a model that learned template artifacts can suddenly lose performance when the template changes. This is a classic example of shortcut learning, where the model appears to understand the task, but is really using superficial cues. Another failure mode is domain shift, where the model is trained on one type of text, such as internal incident tickets, and then applied to another, such as customer support chats, where language style and vocabulary differ. Beginners sometimes assume text models are general because language is general, but in practice models are sensitive to the distribution they were trained on. Evaluating for drift includes monitoring vocabulary changes, out-of-vocabulary rates, and shifts in score distributions over time. In security contexts, drift can be normal because operations evolve, so evaluation should include ongoing monitoring, not just a one-time test set. Recognizing drift as a failure mode helps you maintain systems responsibly. Bias and failure modes also intersect with privacy, because text can contain sensitive details that influence model behavior in ways that are unacceptable. If a model learns that certain names or identifiers correlate with incidents, It may be using sensitive personal or organizational information as a shortcut. This can create unfair targeting, where certain users or teams are flagged more often because of historical patterns rather than actual risk. It can also create privacy risk in explanation, because showing the influential tokens might reveal sensitive details to people who should not see them. Beginners sometimes treat explainability as automatically good, but in text systems, explainability can leak sensitive content if not handled carefully. Evaluating NLP responsibly includes checking whether the model relies on sensitive tokens and deciding whether those tokens should be masked or excluded. In cloud security, where logs and tickets can include PII, governance requires that the model does not become a mechanism for spreading sensitive information across teams. This is why evaluation is not only about accuracy, it is about safety and compliance. A model that performs well but violates privacy expectations is not a successful model. Another important evaluation concept is robustness, meaning how stable the model's predictions are under small variations in text. Humans can understand a sentence with minor typos, different phrasing, or slightly different word order, but some models can be surprisingly brittle. A classifier might flip categories if a keyword is replaced by a synonym, or if a phrase is shortened, which can happen frequently in real ticket writing. In security text, abbreviations and shorthand are common, and different analysts can describe the same event in very different language. If the model is not robust to these variations, performance in production can be far worse than performance on a clean test set. Evaluating robustness involves checking how predictions change under realistic paraphrases, abbreviations, and formatting differences. Even without generating many variants, you can assess robustness by examining errors that arise from wording differences rather than substantive differences. When you identify brittleness, you may need better representations, more diverse training data, or workflow changes that standardize input text. Robustness is a practical form of safety because it prevents unpredictable behavior from small changes in language. Precision and recall trade-offs become especially nuanced when you use NLP in a pipeline rather than as a standalone decision. Often, text models are used to prioritize or route cases, not to make final determinations. In that setting, you might prefer high recall at an early stage to ensure important cases are not missed, and then rely on later stages, including human review, to filter false positives. Alternatively, you might prefer high precision if the output triggers expensive actions, such as escalating to incident response or blocking access. Beginners sometimes evaluate the model as if it must be perfect, but a pipeline view allows you to assign a role to the model that matches its strengths. Evaluation should therefore include end-to-end impact measures, such as whether time to triage improves or whether analyst workload decreases, not just isolated classifier metrics. In cloud security, this end-to-end thinking matters because the model's value is often in prioritization, reducing the time spent on low-value cases. A model with moderate precision but excellent ranking ability can still be very valuable if it helps analysts focus on the top fraction of cases. Evaluating for operational value is part of evaluating correctly. Bringing these ideas together, evaluating NLP results correctly means treating metrics as tools for understanding trade-offs, not as trophies. Precision and recall describe different costs, and threshold choices determine how those costs balance in real workflows, especially under class imbalance. Bias can enter through reporting styles, jargon differences, and historical investigation patterns, so evaluation should examine performance across relevant segments rather than only overall. Failure modes in NLP include negation misunderstandings, trigger word shortcuts, domain shift, vocabulary drift, and brittleness to small wording changes, and these failures must be identified through error analysis and ongoing monitoring. Privacy and compliance are part of evaluation because text can leak sensitive information and models can learn sensitive proxies that should not influence decisions. The most responsible evaluation connects model behavior to operational outcomes, ensuring the model's role fits the decision pipeline and that stakeholders understand what the model can and cannot promise. When you can evaluate NLP in this disciplined way, you are prepared to build text-driven security analytics that are useful, safe, and maintainable over time.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.